All right, guys, in this rapid review video, we're going to be talking about intermolecular forces of covalent compounds. So we're not going to be talking about ion-ion interactions or ion-dipole interactions. We're strictly going to talk about hydrogen bonding, dipole-dipole interactions, and London dispersion forces. These are the intermolecular forces between covalent molecules. Okay. And we're going to discuss them in terms of how questions about intermolecular forces show up on the free response portion of the AP exam. Okay. And just kind of reviewing, when are you going to have to invoke IMFs or talk about certain compounds IMFs and compare them? Usually when you're talking about the differences between boiling points and melting points, right? But that could come in the form of, molar heats of vaporization and molar heats of fusion. Like, why does it take more energy to vaporize this compound compared to that compound? Or why does it take more energy to melt this compound other than that compound? And whenever you're talking about, why does it take more energy to melt or have a phase change or do this, it's usually about the IMFs. The other times it shows up is when you're talking about the differences in vapor pressure between liquids. So if you have two liquids, at the same temperature, the one with the higher vapor pressure actually has the weaker IMF. So what you want to remember about IMFs and vapor pressure is that the higher the vapor pressure, the weaker your IMFs, because more particles with a higher vapor pressure, it means more particles were able to escape to the gas phase. So more particles were able to overcome their IMFs, so therefore weaker IMFs. And then the other time is when you're talking about solubility. Remember, the rule for solubility is like dissolves like, but you really want to focus on IMFs. You don't want to just say like dissolves like. You want, water's polar with hydrogen bonding. So something else that's polar with hydrogen bonding is going to be more water soluble than something that's polar without hydrogen bonding. So those are the kinds of things you want to look out for. All right. So again, we're focusing on the free response portion. So here is an old free response portion. They gave us the structure of two molecules, and this one's talking about the solubility. So it's asking which one of these two compounds would we expect to be more water soluble. Well, they're both polar and they both have hydrogen bonding. Look, this has an OH, this has an OH, this has an OH, right? So really, they're both polar. We would expect them both to be water soluble, but we would expect this guy right here to be more water soluble, and it's because it has more Fon bonds, right? It has more locations for hydrogen bonding. Now remember, Fon bond is just our term to remember what types of bonds will yield hydrogen bonding. So don't use Fon on the AP exam. But when you're talking about solubility, it's about intermolecular forces. They both have hydrogen bonding, but this has more places for hydrogen bonding. So this is going to mix better with water than this is. They're both going to mix with water, but this one's going to mix better. More locations for hydrogen bonding. Okay. And here's the actual scoring guide answer they were looking for. Now, you don't have to write this word for word, but notice they did mention how many OH groups this had compared to that, and they're talking about more sites for hydrogen bonding. Okay. All right, so we move on to the next one. So in this one, there's a lot of, we can talk about hybridization, we can talk about shape, we can talk about that this bond angle is not 180, it's really 120 because it's trigonal planar and all that stuff. But really in this, I want to focus on this question here. You had to draw one of the hydrogen bonds. And remember, you want to go from negative dipole to positive dipole, but at least one of those dipoles has to be a result from a Fon bond. So as you can see this diagram, this is oxygen and this is hydrogen. This is hydrogen. So you wouldn't want to draw a dot from hydrogen to hydrogen. That would be positive dipole to positive dipole. Oxygen to hydrogen would work. Now, they say just draw one. So make sure you just draw one. But I have multiple drawn on the key here. So, right, here would be a hydrogen bond, that would be a hydrogen bond. Now, the hydrogen from water to the nitrogen atom here, that would be a hydrogen bond. Now, you could call this a hydrogen bond. This is an oxygen double bond here, and this is hydrogen from a water molecule. So that interaction would be called a hydrogen bond, but the strongest would be, right, Fon bond dipole to Fon bond dipole. So that interaction is probably going to be stronger than that interaction, but that should count as a hydrogen bond as well. Okay. So here we have two compounds. They have the same shape, right? Trigonal pyramidal. That lone pair is making the molecule asymmetrical. So they're both going to be considered polar. Now, what we should remember about nitrogen and chlorine is they both have very similar electronegativity values. So if not equal, some charts might call them equal electronegativity values. So this one might be polar, but since that bond really isn't that polar, this is going to have very weak dipole-dipole interactions. But notice this does have your Fon bonds, right? So this is going to have hydrogen bonding. And notice again, this is asking about solubility. Why is this one highly water soluble and this one nearly insoluble? Well, nearly insoluble would mean in water would mean it's, kind of non-polar. And even though it's asymmetrical and it will have a dipole moment, meaning it is polar, it's not going to be a very big one, and so it's not going to be as water soluble. Okay. So again, like dissolves like, and again, you don't want to use Fon. That's just for us. But remember, NCl3 is not very polar, and it would have weak dipole-dipole interactions in London dispersion, whereas this has strong dipole-dipole interactions, hydrogen bonding, in fact, and London dispersion, and so that's why it's going to be more water soluble. Okay. Now we go to here. This is more sites for hydrogen bonding, right? This really only has one site. This has multiple sites, one there and one here. But it's not talking about solubility in this case. It's talking about the melting point. But still, when you're talking about melting point and you're comparing them, it's still about the IMFs. So multiple sites for hydrogen bonding, and that's why this has a higher melting point than that. Okay. Here we have to list the IMFs. It's always good when you're comparing molecules to, even if you're not asked for it, list the IMFs that they each have. Okay, so if we look at HBr and HF, dipole-dipole interactions in London dispersion for HBr, but hydrogen bonding in London dispersion for HF. Now, you can get away with listing all three for HF, but since HF is pretty simple, it's the only dipole-dipole interactions it has are hydrogen bonding, so you can get away with just saying hydrogen bonding in London dispersion. But anytime something has hydrogen bonding, go ahead and say hydrogen bonding, dipole-dipole, and London dispersion, okay? And again, this is talking about why the molar heat of vaporization for HF is higher than the molar heat of vaporization for HBr. And the reason is HF has stronger IMFs. And then you would want to explain that the hydrogen bonding and London dispersion forces in HF are stronger than the dipole-dipole interactions and the London dispersion in HBr. Okay, but that doesn't always mean that the thing that has hydrogen bonding or the thing that has dipole-dipole interactions is stronger than the thing with only London dispersion. If we get here, we notice that CS2 has this boiling point, but COS, which is polar, has this, and it's a lower boiling point, and CS2 is symmetrical, so it's non-polar. So how does a non-polar thing have a higher boiling point than the polar thing? Well, it just means the London dispersion in this is stronger than the dipole-dipole and London dispersion in that. Okay, so don't be afraid of saying the non-polar thing has a higher boiling point. It just means it has greater London dispersion. Okay, so we list their IMFs. Okay, and yes, this one has more IMFs, I guess, to list, but it doesn't mean they're stronger. Okay, so the London dispersions in CS2 are stronger than the combined dipole-dipole interactions and London dispersions in COS because CS2 has more total electrons. Okay, so that is the rapid review. Go do the Schoology assessment.